I think we're good. All right. Sweet. So this is, before I get into the 2.2 lesson, which, let's see. Yeah, okay. So it doesn't say 2.2, it says empirical rule and normal distribution on your notes. Before we talk about that, just going to talk about density curves in general. So this is not on your paper, but just something to intro it. So we can have all these different histograms, these different plots, and I've done this before to kind of show if it was skewed or not, kind of trace the top of the lines, and we can kind of say, like, this one is like, I don't know, bimodal, it has different clusters, this one is skew right, and this one is like roughly symmetric. And we could say different things like that. A density curve, what it does is it just shows the probabilities, like all the probabilities that you could have, like in an outcome. So like, if I was to do the density curve on this one, I could say, what's the probability of me getting 57 or less? Which I think this one was like the amount of time between Old Faithful geyser blasts out at Yellowstone National Park. And so like, what's the percent likelihood of me getting 57 minutes or less? And I could find the probability underneath that little section. Or like, what's this one? The number of employees at Fortune 500 companies, I think. And so how many have 75,000 employees or more? And I could tally up those and get them over a total. A thing about a density curve is that the area, so the main thing is that the area under the curve equals 100%. Or if we're talking in decimals, which a lot of the time percents are in decimals, it would equal 1. So no matter what, whatever my curve of my data looks like, the area underneath it is going to equal 1 or 100%. So that's the probability of like everything under my curve is all my data. So like, you can have density curves that look like this. You could have some that like just are like this. You can have different ones, but it just means, it just gives us a model of like all the different probability outcomes, and we can get the probability of something happening. The one that we like to talk about and is a normal distribution. So this is your paper. So a normal distribution is just a perfectly symmetric distribution. So normal distribution, I'll just say it is symmetric. So, well, maybe I shouldn't do that. So it's symmetric bell curve. Because you can have symmetric data that's not, it just has one nice curve, and it goes up to the mean and it goes back down, which is the picture right below. So a normal distribution, symmetric bell curve data, and we like to work with data like this, or we want to make our data look like this. Dealing with stuff that's like skewed or that's like clustered and stuff is kind of hard, and so we like to do probabilities that look more like normal distributions. Okay, so let's actually fill out this middle part first, and then we're going to come back up to the top. Okay, so we got 2,000 freshmen at a university took a test, and the scores were distributed normally. And so if it tells you that they're normal or approximately normal or anything like that, I want you to have a picture in your mind that looks like this, a nice bell curve distribution. It said they had a mean of 70 and a standard deviation of 5. And so we want to label where those things are at. So our mean is directly at the middle of this distribution. So if I drew a line right down it, that would be our mean, 70. Okay, and then a standard deviation, the definition of standard deviation is like a distance that our data typically is from the mean, our average distance from the mean. And so one standard deviation doesn't take up the entire graph. It actually just kind of goes, like on this distribution, it goes like this far out. So this would be like -1, and then I'm going to do the little standard deviation symbol. This would be +1 standard deviation. This
just do it as like 75.
Yeah, so I was going to fill that in underneath. So yeah, that'd be 75 and 65. And so if I went 2 standard deviations from the mean, that would be me at...
Is that an S?
That's like a little symbol that is like a circle with like
Oh.
a hat sort of thing. It almost looks like a person's wearing, well, I don't know what, a music note, or I don't know. I think about it as a little stick dude with a, I don't know what he's doing. Okay, so I got 2, if I go 2 standard deviations above the mean, so 70 plus 5 plus 5, I'd be at a person scored 80 on the test. And then I'll do one more. Here's the third mark. So the third standard deviation would be a score of 85. So this was kind of a hard test guess. And so I'll do it down here too, like -2 standard deviations would be at a score of 60, and then you have -3 standard deviations at a score of 55.
Does that mean that nobody made below is 55 or above 85?
So we're gonna calculate that. Yeah. So what's the, if I had like an actual distribution that was normal with a mean of 70, standard deviation of 5, yeah, like we can calculate what's the probability of someone getting above an 85 or below a 55. So yeah, it's very unlikely that like someone was above an 85 or below a 55, but like there is a probability. Okay, but I just wanted to look at this thing first and kind of see it. So this would be my mean, and then I go 1, 2, 3 standard deviations each way, and I can put the marks at each little spot. Okay, so I just made a little mark for myself, so y'all don't have to necessarily write this. I just wanted to point something out here. So if I was to do the z-scores for each one of these, then I'm going to get, like, what would the standardized scores for each of those look like? So if I did it for 70, the z-score, which is really tiny, written on the back wall there, it says normal distribution on a poster, and so I'm supposed to do my value, so I'm going to do for 70. Value minus the mean divided by standard deviations, which is 0. So my mean z-score is 0 because a z-score is how many standard deviations you are from the mean. So if you have a 0 z-score, it means you are at the mean.
Can you have a negative?
Yes, you can have a negative. So like if I did 65, it would be 65 minus 70 divided by 5. So 65 minus 70 is negative 5 divided by 5 would be
Negative 1.
that would be -1. Which one thing, so that would be -1, a -1 z-score. So that is z equals -1 means that you are -1 standard deviation from the mean. So z-score and the number of standard deviations are the same. You can also have a decimal. You could be -0.2 standard deviations, +1.4 standard deviations. So the z-scores, like this would be a z-score of -2, a z-score of -3, a z-score of 1, a z-score of 2, and a z-score of 3. Because it just means what I already wrote right here. It just means the number of standard deviations you are from the mean. Like I could do this one, 85 minus 70 divided by 5. So that's 15 divided by 5 is 3. So the number of standard deviations you are is the z-score. So that would be z equals 3. Means you are this far above the standard deviation, this far below. Okay, so let me do something else that's going to help us in the long run here. So I'm going to give you a little table of digits that might look a little weird at first. But
Oh,
it's
this is
really
from our formula chart.
Yep, this is on your formula chart. Alright, so I'm going to go to it so that the people at home can see as well. So yeah, I'm on my formula chart, and at the bottom of the formula chart there's some tables, and we're going to use the first one here that is called Table A, and it has a normal distribution with a z on it. And what these values are, if I could try and explain it here. So let's do a negative, or how about we do this one first? So let's go to this page, and if I'm on the so one side of that sheet that I gave you is positive numbers and one side's negative. If you look on the side, the left side here. And so if I'm reading this table, I have the tenths digits on the left side and then the hundredths on the right. So if I wanted the number like 0.55, so I'd go to 0.55 would be this number for 0.55, would be that value. That would be, these are z-scores, so that would be a z-score equal to 0.55.
And what's the 0.7?
Yeah, I'm going to explain that here. So what does that value mean? So, oops, I didn't want to take a picture of that. Clear it. Okay, so let's look at a z-score of 0.00 first. So tell me again, what does a z-score of 0 mean?
It means that
It's on a mean.
You are the mean if you have a z-score of 0. You are 0 standard deviations from the mean. You are the mean. And it says 0.5000, or that would be otherwise known as 50%. So it says 0.500, that means 50%. These are in decimals. These are all percentages in decimals. So what this is it's saying if I had a z-score equal to 0, all these numbers calculate the percent of this graph that's less than. So right at a z-score of 0, 50% of my data is this way, which means 50% is also that way. Which that makes sense, right? If I'm at the mean, 50% should go one way, 50% the other. So that's what's happening here. So then let me try and get a couple of other numbers here. So I'm going to try and fill out our... Oop, I did not want to take that picture. Okay, so let me fill out this table. So in a normal distribution, what percent of the values lie below the mean?
50%.
50%. That's what we just did. Like, if I go back here, a z-score of 0, I have 50% less than that, 50% greater than, because it's supposed to add up to 100. So 50% is one way. So then above the mean would also be 50%. Okay, let's try and calculate what would be within one standard deviation of the mean. So what percent of our graph is from -1 standard deviations to +1 standard deviations? So this is I haven't done it like this in the past, but I think it'll help us for when we start doing more calculations tomorrow. But let's look at it. So I want to find what is the value at -1 standard deviations from the mean. So that would be a z-score of -1. So don't say it right now, but I want you to try and find it on this table. So find it on the table, a z-score of -1 standard deviations. What is the value at -1 standard deviations from the mean? So let me just, you try and get it, and hopefully you go to your negative side, and it says -1.0, and then we want to be O. So it would be 0.1587, which let me,
So it'd be 15.87?
yeah, so let me put that into context real quick. Actually, let's go. So someone keep that number, and then +1 would be at, here's +1. It says 0.8413.
So would you do,
So let me go off this page real quick. So don't worry about this right now. So at -1, whoa, what happened to the smartboard? Okay, whatever that was. So at -1, it was like, what was it, 0.1587, and this was 8413. So what those values do is they always take into account the number that's less than. So this was -1, less than, and this was +1 standard deviations, if that makes sense. So like this value of +1 is 84% is all the values less than.
Sure.
And then this one was all the values less than that. Okay, so I'm just trying to get us familiar looking at this table, and it might help. So what is the percent in between there? It's the difference between those two, which is like something like, I guess in this case it's less than 62. Just trying to do that off the top of my head. Is that 61? Or no? Someone do that for me. Or 0.68. Oh yeah, 6826. Okay, 0.6826. Okay, so if I made that, you could say it like that, or you could say it like this, like 68.26%. So the percent between -1 and +1 standard deviations was 68.26%. I could do that for every single one of these values. We don't use that close of decimals. We actually kind of like to round. There's like this rule in statistics that we like to use for quick calculations. So if I am 1 standard deviation, we like to say that you would be 68% of the data.
Is there like a significant, like, is there like a certain number of like significant figures you're supposed to show in the statistics?
Like if you're doing a decimal, you need like 2 or 3 or something like that. But right now if you're just giving a decimal answer, think about going like 2 or 3. Okay, let me mark my graph here. So from -1 to +1, we're supposed to have 68% total between there in the middle. So this is kind of a rule that we have. From -1 to +1 standard deviations, it takes up about 68% of my data. So if I told you that our last test had an average of 82 with a standard deviation of 5, that means about 68% of our people, if the distribution was normal, 68% of the people were plus or minus from there. So like 87 to 77. So let me go back and fill this out. So within 1 standard deviation is 68%. Within 2 standard deviations is 95%, which you could look up on the z-score table, and it would be it'd be a decimal, but it'd be close to 95. It'd probably be like 95 point something or 94 point something. So from -2 standard deviations to +2 standard deviations is 95% of my data. So now I'm getting a lot of my people. And then from 3 standard deviations is 99.7% of your data. If you are in a normal distribution. If you go 3 standard deviations, negative and positive, you're supposed to be gathering about 99.7% of the people, or whatever it is. So let's try and look at this. So let me fill out this table here. So let me make another little mark. Okay, so I'm gonna actually split this up by a little section here first. So if I'm from -1 to +1, I'm supposed to be 68% of the data. So that means in this little group, actually I'd be taking away some work from you if I did that. So actually I'm gonna stop, because I think that's the questions below. So let's try and do this out. Okay, I want you to try and do A. So I need to stop doing too much. So what percent, so I want you to do A, and then let's do that. Let's do B. All these problems can be solved by doing the 68, 95, 99.7 rule. So I want you to try and use those numbers. You don't have to use that table of digits I gave you. I want you to use the 68, 95, 99.7 to find out these little values here. Kind of scattered right now, but we're getting there. Okay, so let's do A, and then we're going to stop, and we'll do B, do C. So the way I want you to think about these is, right now, all we know how to do it is just by doing it by the standard deviation. So the first problem is, what is the percent from 65 to 75? And that should have been, we're going from -1. So basically I'm going from -1 standard deviations to +1 standard deviations. And that is that rule, that 68% of that data is from -1 to +1. So if it gives me values directly on that number, then I know these are just, if this data was perfectly normal distribution, I would have 68% from a score of 65 to 75. Because it was -1 to +1. So what percentage of the scores are between 60 and 70? So how many standard deviations is 60 at? Yeah, the z-score or whatever would be -2 standard deviations. And 70 is the mean of 0. So what's the amount of distribution from -2 to 0? Using our 68, 95, 99.
95%.
What's up?
95%.
Okay, so 95 is from -2 to +2 is 95. So yeah, so half of that from -2 to 0, this is perfectly symmetric. So what I'm going to do, if it's half of it, is I can take that total of 95 and divide by 2. So if I like was showing, if I was doing some work, like 2 standard deviations would be 95%, but it's cut in half. So I think that's like 47.5%. And I might need to be better at this. Like you could also write that as 0.475, or you could write this as 0.68. Like getting used to seeing it in a decimal as well. So these are the same number, those are the same number. Okay. What percent of the scores are between 60 and 85? So 60, which we just did in that last problem, is -2 standard deviations. And 85 is +3 standard deviations above. So maybe I'll look at this one with you. So from -2 all the way to +3. So I know from -2 to 2 is for sure this 95%, and then I just need to find what percent is this other little section. So I know for sure that I have 95% in there, and I need to add what is this little value here. Okay. So any ideas?
97.35.
What's up?
97.35.
Okay, how'd you get 97.25?
Because I did, it would be the 99.7 divided by, that by 2 and added it to the, 47.5. Here, I have another one.
Oh, I see what you did. Yeah, you did like this,
Yeah.
this part.
And then I added it to the.
Okay. All right. Yeah. So like from 3 standard deviations would be 99.7. So you could get like this little half, and yeah, cut it in half, and then add it to that one. How about before we move on any farther? How about let's just write each of these little sections before I like confuse y'all too much here. So let's get this little section here. So I'm supposed to be 68% on here. So that should be 34% in each little category. Would y'all agree? Like those need to add up to 68%. Okay. Then I have 68, and then I'm supposed to go to 95 on each side of that. So what you could do it a different way. I'm gonna do 95 minus 68, which is
I
something.
think there are 13.5 on each side.
What's that?
I think it is 13.5 on each side.
On that one?
Yeah.
Yeah, I'm like, can't do my math right now. I'm
It's
too
27.
scatterbrained. Okay, yeah, 27. So yeah, 27, so then 27 cut in half would be, yeah, that's good. It'd be 13.5% on each of those. Because all of those, if you add all 4 of those together, that should be 95% in total. And then the last one, these little sections here, you could do it multiple different ways. Maybe I'll do it kind of the way Jada Lee was doing it. So this, in total, should be 99.7 divided by 2. So this calculator's not turning on, so I need someone to help me out with that. 99.7 divided by 2.
49.85.
Okay. So like this whole section would be 49.85. And so take that minus 34 minus 13.5.
2.35.
Okay, that sounds pretty reasonable. 2.35. And then you can even get what's the percent of getting what, like, if you scored above an 85, what was the likelihood of that, or like how above were you? So basically, I would just do it like 99.7 is in there. So there's, what is that? 99.7, there would be 0.3 on either end. So I think it would be like 0.15% on either side there. So there's not even a full percent chance that you, so if you scored like a 90 on this test, if this was an actual sample of data, and you scored 90, you'd be like doing really, really well. Like you were like beating the odds compared to everybody else. Here. Okay, so looking at these, all these just working off this 68, 95, 99.7 from 1 to 2 to 3 standard deviations. So this, let's go back and let's see what we can do from here. So yeah, 95, and we would just add this 2.35%. So it'd be 95 plus 2.35, which should be like that answer for C. Should be about 97.35%. What is the percentage of scores less than 55? So I think we calculated that as something like 15.15% chance of happening. Like a super small. If that was a decimal, it would be 0.0015. Okay, what percentage of scores greater than an 80? So just looking at this a different way. Let's say I didn't have this distribution of exact numbers right here. So what if I wanted the numbers greater than 80? So the way I like to think about it is if I wanted to get the numbers greater than 80, which is 2 standard deviations. So in between 2 standard deviations is 95%. So that means the leftovers outside of that, so outside of -2 to +2 standard deviations is 5% of my data, is what that would mean. Like inside is 95%, on the edges is 5%. And so if I want to get what's the percent greater than one of those, I'm just gonna divide that in half, and there's a 2.5% chance that it's greater than 80. Which, let me just go back to this real quick. I think those two combined is 2.5%, so it kind of works out. Okay, so just using the 60, 68, 95, 99.7, and we can try and find all these little half values or greater than values, and go from there. Okay. F and G are just using estimates based on your probability. So we have these percent chances of like 68% of the students were in this range, 47% there. So like on F, how many students scored between a 60 and 70? So we got the percentage of that up here was 47.5%. But we're trying to get exactly how many students got that number. So I'm pretty sure on the paper it says that there were 2,000 students that took the test. So we said it should be 47%, and if I have 2,000 students, I need to do what is 47.5% of 2,000. So when you're multiplying, you use the decimal number, which is why knowing these decimals, a lot of the times in statistics, you're just given the decimal. You want to just say the decimal answer. You don't really have to say the percentage. So like if I'm trying to get the actual number of students, it would be 2,000 times 47.5%, which I don't have a calculator.
950.
950? Okay, so that should be, sounds about right. 950 students. Same thing for how many students scored between 55 and 60. So 55 and 60 was about 2.35% of my students. So I would do 2,000 times 2% would be 0.0235. 27 students? 47, okay. 47. So 47 students. Sounds about right. Okay, so kind of using the percentages with like, okay, this is a clump of students in here, this is an amount of students here. But this is just using the normal distribution to try and get probabilities of you being in this category or this one, this one or this one. So this this normal probability table is what a z-score. This is why we kind of use a z-score, is because if I do the z-score of something, it puts it in this nice table like this for me. So when I do a z-score, it gives me this normal distribution, and I can find probabilities that, what was the probability of you having a 1.2 z-score? What was the probability of you having, so like 1.2, what was the probability of you being a negative 1.6 z-score, or stuff like that. So we're going to get into how to do the decimals Friday, but just kind of introing the data. So you've got 68, then you go 95 from 2 to 2, and then in a normal distribution, 99.7% of your data is plus and minus 3 standard deviations. So by the time you go 3 standard deviations out, you should be getting pretty much all of your data. Not guaranteed all of it, but most of it. So yeah, just working in those little differences. Okay. So yeah, they can ask. We're gonna get how to get these using the table, and we're gonna do it using the calculator. But if you have one of these perfect numbers at 1 or 2 or 3, you can just do it using this too. So you don't have to use it this way. You can always use the table or always use the calculator. But these are just like little quick hitters, or it's just a rule just hit on a lot. So it's kind of a major thing. All right. So I think going into the table, we're gonna talk more about how to use it tomorrow. So don't be too concerned about looking at it. Yeah, I felt like I felt pretty scattered in the way I was explaining some of that. So, we have 10 minutes. Please let me help you if you are confused on what I'm saying. So maybe I'll leave it there and then I'll come around and help y'all individually because I felt kind of like scattered in it, but you might feel okay. Let me see.